Right at the very heart of reality, there's a mystery. It's a puzzle that suggests the universe we think we know might be governed by some kind of hidden order, a secret logic hiding just beneath the chaos we see. Today, we're cracking open the case file on one of the oldest and deepest questions in all of physics. And this is where it all starts, with Albert Einstein's famous complaint. He was just deeply bothered by the new theory of quantum mechanics. I mean, it suggested that at the smallest scales, the universe was ruled by nothing more than pure random chance. He just couldn't accept that. He believed there had to be something more, a deeper layer of reality we just weren't seeing yet. And really, that's the central question of our whole investigation today. What if Einstein was right all along? What if the roll of the quantum dice is actually fixed? What if everything that looks like pure chance is really the result of some invisible, deterministic process working behind the scenes? To figure this out, we need to go back in time. We have to visit the scene of a century-old scientific crime, if you will, a fundamental paradox that sits right at the core of quantum physics. This is it, the infamous measurement problem. So picture this. Before we look, a particle can be here, there, and, well, everywhere, all at the same time. It's like this ghostly wave of possibilities. But, and this is the crazy part, the instant we try to measure it, that whole wave of potential realities just collapses into one single concrete outcome. But how? What force is making that choice? For almost 100 years, the physics community has had an official story. It's an explanation that's been taught to generations of scientists, but it's one that just maybe isn't the whole truth. So, let's bring in our prime suspect. It's the most widely accepted theory for this quantum mystery, and it's called the Copenhagen Interpretation. The Copenhagen Interpretation, well, it basically just says that's how it is. Before you measure it, a particle's position or its momentum, it just doesn't exist in any definite way. The very act of looking forces it to pick a state, and that choice is supposedly completely and utterly random. There's a rule, the Born rule, that gives us the odds for each outcome. It's like a cosmic bookie, but it never, ever explains the actual mechanism behind the win. And that's the real problem, isn't it? The Copenhagen view, it describes what happens, but it gives us zero explanation for how it happens. It's like a detective describing a crime scene but having no theory of who did it or how they pulled it off. This leaves a massive hole in the story, and it makes you wonder, is there a ghost in the machine? Some kind of hidden process pulling the string? This is where our investigation takes a really interesting turn. A new lead has popped up. It's a theoretical framework that proposes a very different culprit for what's going on. It's called Fractal Resonance Cognition, or FRC for short. Okay, so FRC suggests something pretty radical. It says that the randomness we think we see isn't fundamental at all. Instead, it's just an illusion that's born from incredibly complex but, and here's the key, ultimately deterministic patterns. The name itself is a clue, right? Fractal, because these patterns look the same at different scales, and resonance because the system is guided by these harmonious interactions. Kind of like how a guitar string vibrates at very specific, clear frequencies. So at the heart of this idea are these two concepts, vortex-like attractors and fractal scaling. Think of attractors like drains in a sink. No matter where you put a drop of water, it's going to eventually spiral down into them. FRC says quantum states are guided by similar kinds of attractors. And fractal scaling just means that these spiraling patterns look similar no matter how much you zoom in or out. This slide is a fantastic way to visualize this. On the left, you've got a nice, simple, totally predictable wave. Easy stuff. But on the right, well, that's a whole different beast. That's a fractal wave. It's got these jagged, complex patterns that just keep repeating at smaller and smaller scales. FRC is basically suggesting that the hidden dynamics of the universe look a lot more like the wave on the right, structured, incredibly complex, and self-similar all the way down. Okay, so if it's not a random collapse, what's really happening? What is the mechanism? Well, FRC theory proposes a very specific process, a howdunit, that directly challenges that old official story. This table just lays it all out, side by side. Where Copenhagen sees this violent, random, probabilistic collapse, FRC sees something much more elegant, a deterministic phase locking. So instead of the system just randomly breaking, it's gently guided into a stable configuration through resonance. It means randomness isn't some fundamental feature of our universe. It's just what we see on the surface of these incredibly deep, complex, underlying patterns. So let's go back to that drain analogy. This is what's really essential to get. The ball doesn't just randomly appear at the bottom of the drain, right? No, it follows a very specific guided path. FRC is proposing that a quantum system does the exact same thing. It's gently pulled along a totally deterministic trajectory into one of several possible stable outcomes. These are the attractors. Now, this is a fascinating theory, but any good detective needs evidence, hard proof. If this hidden, deterministic process is real, it has to leave some kind of clue behind, right? A fingerprint that we can actually find. So the question is, where do we look? And this is the cool part. FRC makes very specific, testable predictions. It says if we look closely enough at quantum data, we should find 3 key signatures. First, evidence of specific fractal dimensions, which is basically a mathematical measure of a pattern's complexity. Second, we should find energy levels that are spaced in harmonic intervals, just like notes in a musical chord. And third, these things called power law correlations, which are a dead giveaway for scale-invariant fractal patterns. And this right here, this is what that fingerprint might actually look like. This graph shows a power law correlation. See how it forms a straight line on this special kind of plot? Finding a relationship like this, hidden in all the noise of a quantum experiment, well, that would be like finding a suspect's DNA all over a crime scene. It would be a smoking gun. And what's really exciting is that scientists know exactly where to look for it. The theory proposes that experiments using custom-built microwave cavities or advanced laser techniques like high harmonic spectroscopy, these could be the forensic tools we need to finally uncover these fractal signatures. So this isn't just philosophy, you see. It's a real, testable hypothesis. Which brings us right back to our central mystery. For a whole century, we've pretty much accepted that the quantum world is fundamentally random. But what if it's not? What if, hidden beneath all that chaos, there's an incredibly intricate deterministic machine at work, guiding the entire universe along these beautiful fractal pathways? The case is far from closed, but for the very first time, we have a new suspect. We have a clear motive. And now, we have a fingerprint to search for.